Hello, my name is Ethan Chitness, and this is Lab 1 Constant Velocity. In this lab, I will be analyzing the motion of a ball rolling across the floor, and we will be analyzing Newton's second law of motion, F equals ma, or inertia, that an object in motion will stay in motion unless acted on by an outside force. And an object with constant velocity will change at position at a constant rate because it has zero acceleration. The result of this lab was in my position versus time graph, we had a constant slope, a constant downward slope. If there's an equal number of pushes and pulls on the object, it will have zero net force and no acceleration due to that. If F net is equal to ma in Newton's second law, and F net is zero in this case, zero is equal to the mass times acceleration, and 0 divided by mass is equal to 0. So therefore 0 is equal to acceleration. It will have a constant velocity. Velocity is the derivative of position as well. So if we have a constant velocity graph, which is a flat line, then our position is integrated from that velocity, and it will be our slope of our position, which will be constant. In this lab, the system was the ball, the surroundings are the floor, which cause friction, and air, which causes air resistance. Those are errors we will get to later. And the initial conditions are negative 0.604 meters as our starting position, negative 0.625868 meters per second is our velocity. It will start at 0.7 seconds because the ball has to roll in a frame, and the mass of the ball is 0.0221 kilograms. As we can see in the video, we have a constant downward slope in our x position. Our y position does not matter because we're only analyzing horizontal motion. And we can see the constant slope, and we can follow that down the graph as the ball rolls across the screen. So in the video, I rolled a ball across smooth wood floor to minimize friction, simulating a constant velocity. Using the tracker, I then went through each frame and clicked the ball's position to create the graph. And then in GlowScript, I took the average velocity, which is final position minus initial position, divided by the change in time, and I used that as my velocity for GlowScript, which I then created a model to predict where the ball should end up. To do this, I entered my initial conditions, and then I set to while t is less than 2.687, which is our final time in this experiment. I then took the ball's current position, and I updated it by adding velocity times delta t, which should then update the graph with a new position at that time interval. As we can see here, we have our initial conditions, our position, velocity, mass, our starting time, and the time interval for each loop of the code. We have zero net force because we're at a constant velocity, and we have position plus the velocity times delta t. And as we can see, that creates the graph that looks very similar to our experimental graph. And you can see them both on one graph here. The red line is predicted and the blue line is experimental. And the experimental graph is slightly curved underneath the predicted graph. That is due to the friction slowing down the ball, which we'll talk about in errors in a second. Both go from positive to negative at relatively the same starting position, or exactly the same starting position and ending position. And the average velocity of our experiment is very close to the actual slope of our predicted x, which is our actual constant velocity. Errors come from friction of the floor and friction of the air resistance, because without a vacuum, it is impossible to have zero friction. And in this case, the wood floor helped, which was smooth, which helps reduce friction and minimize it, so that way our velocity can stay relatively constant. Furthermore, when I entered it into the tracker, I had to click on the ball in every frame at the exact center of the ball to create a perfect graph. And it's very hard to get at the exact center of the ball every single frame. Therefore, that's human error when actually using the tracker to not have a perfect graph. However, it was very close still. If we flip the axes of our graph, we would have a graph that goes from bottom left to top right and would have a positive upward slope. That is because we're going from negative to positive if we flipped our axis instead of positive to negative. And our velocity and our slope would be the exact same, except we would flip the sign because we're going in the positive direction this time instead of the negative direction. So it would be positive of what our initial velocity, which is, it would be positive 0.625868 meters per second. And the pushes and pulls, there are a single initial push And then the pulls against it are the floor and air resistance, which we cannot get rid of due to there being some friction. However, it mostly cancels out because our velocities were very close in this instance. However, there is slightly more pull than push. And that is all.